We're going to look now at viscosity, a term you've probably heard before, even if you're not sure what it is, and laminar flow. So laminar flow is characterized by the smooth flow of fluid in layers that don't mix. So imagine a river smoothly going downstream. If you place a bunch of kayaks equally spaced in the river, all those kayaks move downriver, they don't bump into one another. Turbulent flow is characterized by eddies and swirls that mix layers of the fluid together. So in a turbulent river, a turbulent flow, you place a bunch of kayaks equally spaced and let them down, they would start bumping into one another and start moving, spinning around in circles. The water does not flow in a laminar fashion. Now, laminar, you think of laminate layers. So turbulent flow is characterized by eddies and swirls. So we can actually talk about flows. Let's look at laminar flows for a moment. We'll go back to turbulence in a little bit. But laminar flows, fluid likes to flow, tends to flow. That's why we call it a fluid. How easily it flows is given by its viscosity. Its viscosity, your book uses the eta, the Greek letter eta, looks like a fancy cursive N with a long second tail. Eta is a measure of viscosity, right? That's the representation of viscosity. And think of it this way. I have a barge, a flat piece of wood on top of a calm lake or swimming pool, and I push that barge along. Well, the barge will bring with it, because of adhesive forces, the water that's right beneath the surface of the barge. So I push the barge, I apply some force on the water, I push the barge ahead at some velocity, and the water immediately below the barge will also move forward at that velocity. However, at the bottom of the pool, or the bottom of the still lake, the water has no, the ground, right, the base of the lake isn't moving, so the water touching the base of the lake won't move. So you'll have a laminar flow. Each layer of the water will be at a different velocity, all the way from my initial velocity of the barge down to zero velocity, which is the velocity of the lake floor, the pool floor. How easy is it to move this barge is a measurement of the viscosity of the fluid. Right, we're applying a shear force here. We have the water is some height L here, some length L. We're applying a shear force compared to that length. The easier it is to move the barge, the less viscous the water is. So imagine doing this in a swimming pool filled with syrup. Right, you would have to produce a very significant force to create a forward velocity in syrup, and much less in water or motor oil or whatever. So the viscosity depends upon the force needed to push ahead, right? The bigger the force needed for a given velocity, the bigger the viscosity. It depends on the length here of the layers, how thick, right, the fluid is here to get between those two. It's inversely proportional to the speed for a given force, and inversely proportional to this area of that barge that's touching the water. So if viscosity is small, that means that the velocity is very large for a given force. If a fluid without any viscosity, the object actually would move without, you just apply a little bit of a force, and that object would move at a constant speed. There would be no resistance to motion in a fluid with zero viscosity. So here's the relationship for viscosity, and your book gives a bunch of examples of different fluids and how viscous those fluids are. The flow rate of a system depends on pressure differences. So if you want water to move from one area to another area, you have to supply a pressure difference. For example, a garden hose, right? You turn on the garden hose, the high pressure that comes from the water tower pushes water out to the atmospheric pressure at the end of the hose. But that flow rate isn't just due to pressure differences, it also has a resistance to that depending on the tube that it's going through and the viscosity of the material. Right? So we want to look at the resistance R, where R is the resistance of an incompressible fluid to a laminar flow. Well, how do we figure out what the resistance is? Clearly it has something to do with viscosity, right? Because it's going to be harder to push syrup through a hose than water. And we have here a relationship for that resistance. So the resistance depends on viscosity. Eta is here, it's a constant 8. L is the length of the tube. The longer the tube, the bigger the resistance. Pi, again, that's just a factor of the fact that we're assuming that the tube is round. R to the 4th, where R is the radius of the tube. So the bigger the radius, this very quickly goes to a very small resistance. So big tubes have very small resistances. Small tubes can have very large resistances. So the biggest effect on this actually isn't the flow of the viscosity, but the radius of the tube. So plugging this into the equation above, we have the flow rate is equal to the difference in the pressures times pi r to the 4th over 8 eta times L. This is called Poiseuille's law. It's French, Poiseuille's. That's how that's pronounced. Poiseuille's law relates the flow rate. So if you want to get a specific flow rate, right, if you want to push water from one place to another at a specific rate, or oil, or whatever, you need to take into account the resistance to that flow depending upon the viscosity. So the bigger the viscosity, the smaller the flow rate. How far do you have to send that fluid? So the length of the pipe is inversely proportional to the flow rate. And that allows you to pick the diameter of the pipe necessary to get that flowing. So think of the pipeline things that they're talking about in American politics, right? The pipelines that are trying to go through from the Canadian tar sands down to the refineries in Texas. You have to determine, right, how to get the flow of natural oil, crude oil from one place to another, depending on the viscosity of the oil that you're pushing. Different oils have different viscosities, the length of the tube you're pushing it in, and that allows you to pick an acceptable radius for the tube. You can't pump, of course, a very, very small diameter tube is not going to give you very many gallons per second from the tar sands to Texas. You have to have a fairly large tube, which is a huge construction project. Very dangerous to have that much tube unexposed. If there are any manufacturing defects, you can leak oil all over. The tube would be going through Nebraska and a lot of heartland, wonderful farms, and pouring oil on those would not be a good idea. So there's controversy with that. But the people who are designing these piping systems have to take into account a lot of different things to get the flow rate that they want.